Welcome guys, today I'm going to be showing you how to derive one of the most prominent trigonometric identities, and that is of course the angle sum identity for sines. Here it is on board if you don't remember, but it doesn't matter if you remember or not, I'll show you why this works. So we're going to be using a very clean and concise geometric approach here. Here I defined already some random triangle ABC. Here are all the variables defined for future reference and even some lengths which we will be using. And so we can begin with the proof. So the most important step here is actually this altitude, which stems from vertex B down to base AC, and it splits the area of triangle ABC into two right triangle areas. Right, you see we made an altitude, there's two right triangles here. And what it also does is split the angle B into acute angles beta and alpha, which belong to their respective right triangles. And of course, their sum is beta plus alpha. And what do we have with an angle, beta plus alpha, and the sine? Well, of course, it's going to be the area of a triangle. In fact, the area of ABC, which is going to be by the formula 1/2 times two of its sides, we have here A and B, times the angle between them, which is this angle ABC. And of course, ABC is beta plus alpha or alpha plus beta. So we have its area as a 1/2 AB times the sine of alpha plus beta. And this is where alpha sine of alpha plus beta comes in. And now, where do we go from here? How else can we express the area of triangle ABC? We can express it, as I said, the areas of these two right triangles. Where the formulas for the area of right triangle is much simpler, just base times height over 2. We already have their height. So this is going to be equal the area of ABD plus the area of CBD by, of course, the parts whole postulate. And what are the areas ABD and CBD? First of ABD, it's going to be this h, which we had to define. We had to define a variable for the altitude, times AD over 2, so 1/2 times h. AD, well, how can we define AD? Of course, through the tangent of the angle beta. Here we have the tangent of beta, which is AD over h, remember, opposite to adjacent. Therefore, AD is going to be h tangent of beta. And so we have 1/2 of h times AD. AD is h tangent of beta, so it's going to be actually h squared tangent of beta here. And plus CBD, it's basically the same thing. It's going to be 1/2 the height times DC, and it's found the exact same way as we did for B, just with the tangent of alpha this time. So it's going to be h tangent of alpha. And multiplied together, we get 1/2 of h squared times the tangent of alpha. Well, all right. So now we have a very nice comparison. We have that 1/2 h squared tangent of beta plus so on, the other area of the right triangles, is equal to this area of ABC, which we found with the sine of A plus B. What's really messing us up here is we don't have one variable. Here we have h, here we have A and B. So if we write this together, try to simplify, we will not get a unitary expression for the sine of alpha plus beta. However, of course, we have a height, we have right triangles. We can express the sides A and B using a cosine and the height, right? Because the cosine of beta, the cosine of alpha, is going to be this height over their respective hypotenuses, which are A and B. And here I actually have written that B is equal to h divided by cosine of alpha, A is equal to h over cosine of alpha. And here we are basically done. We substitute B and A, these expressions for B and A, into our formula for area, and we get a very nice equation. So from here, from all our steps, we can get that 1/2 of alpha times beta. It's going to be h squared divided by cosines multiplied together. Of course, don't forget our most important sine of alpha plus beta, which we're trying to derive. And that is equal to the sum of the right triangle areas, which we have found previously. And from here, the geometry is completely done. Now it's just a matter of simplifying this expression. From here, we can actually quickly remove the 1/2 already, 1/2 on both sides. We can factor out the h's and remove them on both sides. Let me show you. We're going to have h squared times this sine sum over the cosines product, and it's going to equal, again, factoring out h out of here, h squared. It's going to be tangent of beta plus tangent of alpha. There we go. We can remove the h's. In a similar manner, we removed the halves. Actually, I thought it was not needed to write that. And so we're almost there. We can multiply now the cosine of alpha on both sides and get a unitary expression for the sine of alpha plus beta, which is going to be the tangents sum tangent alpha plus tangent beta times the cosine product, cosine of alpha times cosine of beta. And this is actually just as good an expression as this one, but I mean, why not keep simplifying? Remember that the tangent is just the sine over the cosine. We get that this is equal to the sine of alpha over the cosine of alpha times this cosine product, cosine alpha, cosine beta. Of course, distributive property, we're going to add the sine of beta over the cosine of beta, which is the tangent of beta, right? Multiplied by the cosine product again. And from here, it's very easy to see. Once we multiply, these cosines in the denominator and numerator cancel, both cosine alpha, and the cosine betas. And we finally get that the sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the sine of beta times the cosine of alpha. And so we are done with the proof for the amazing angle sum identity for sines. And actually, if we want to prove the difference identity, the cosine sum identity, we can already use much simpler trigonometric identities in place for us to find all of those. So basically, this is one of the only sum identities we have to prove. To find the cosine sum identities, we can find the double angle identity just as easily by combining two identical terms. We can find the half angle identity in a similar way. For this, everything else stems, which I'll leave as an exercise for you to do. So an exercise for you, now find the cosine sum identity. The cosine of alpha plus beta is equal to what? And try to use this exact formula that we just found in your answer. Do not do it geometrically. And that is it. This was a wonderful proof. And please like and subscribe if you want more of these kinds of videos. And that is it. Thank you for watching.